In the previous sections, we talked about change of internal energy, and we talked about some methods in which chemists can find heat of reaction, using the specific heat capacity, the molar heat capacity, using bomb calorimeters, and things like that. And these are kind of experimental methods in order to determine the heat change, the heat that's released or absorbed when a reaction occurs. Now, what we want to talk about is a concept called enthalpy. And enthalpy is similar to the change in internal energy, but it's at constant pressure. And essentially, what chemists do is they drop out the work term. So delta H equals delta E minus W. Since delta E equals Q plus W, delta H equals Q. And the reason that they do this is that quite frankly, it's easier to calculate the enthalpy, the heat energy, than to calculate the internal energy because you lose this work term. Now, for reactions that don't do a lot of work, basically which are reactions that generate a large amount of gas or use up a large amount of gas, delta E and delta H tend to be similar values. But for reactions that generate a lot of work by creating gas, do a lot of work by creating gas, or have work done on them by consuming gas, delta E and delta H will be different. So essentially, delta H is Q at constant pressure. And a lot of times we perform reactions at constant pressure, and that constant pressure is atmospheric pressure, which just makes it more convenient to monitor the heat energy. A simple way that one can do this is what's called a coffee cup calorimeter, which we do for a heat of solution reaction in the labs here. And here, it's a constant pressure, it's at atmospheric pressure. You perform the reaction in solution, and you monitor the temperature. Based on the temperature change of the solution, the specific heat capacity of the solution, and the mass of the solution, you could find the heat of the reaction. So it's convenient, this is a relatively simple device, and it's relatively easy to measure. So enthalpy is what chemists very often use. And in this section, we're going to look at some of the ways that chemists use enthalpy to calculate different things. But before we do that, we need to talk about enthalpy, which is spelled incorrectly here, but enthalpy and internal energies as state functions. And this may seem like a small detail, but it's extremely important to what we're going to cover in the rest of the section. In fact, the reason what we use in the rest of the section works is because enthalpy and internal energy are state functions. Altitude is a state function you might be familiar with. So here we have Mount Kilimanjaro. Path X is go straight up the mountain. Path Y is to kind of wrap around the mountain. Now, if you look at the person's altitude from here, base, to here, the summit, it's exactly the same. The difference in altitude is exactly the same whether they follow path X or path Y. It doesn't matter, their change in altitude are the same. It's important to note that enthalpy and internal energy, delta E or delta U, are state functions, so the path doesn't matter. I should note here that work and heat are not state functions, and there the path can matter. So we do not want to consider everything as a state function in this chapter, but enthalpy and internal energy are state functions. Now this may not seem like a huge big deal when we cover some of the material later on, but just remember that things like Hess's law and using products minus reactants work because enthalpy is a state function. So here we have this two terminology things that we need to be familiar with. Since enthalpy is essentially heat energy, we need to be familiar with the terms endothermic and exothermic. Endothermic means heat flows into a system. Delta H is positive. Exothermic means heat flows out of a system. Delta H is negative. So as an example of an exothermic reaction, we have the combustion of gasoline. This is clearly exothermic. A large amount of heat energy is being released when we burn gasoline. So that is very important. And in case of an endothermic reaction, we have heat being flowing into the system. So if we look at this cold pack example, the cold pack is a reaction or the dissolving of probably ammonium nitrate into water, and that causes this solution here to get cold. Well, heat is flowing into that system out of the patient. So if someone sprains their ankle and they put a cold pack on it, they want to draw heat away from the person's ankle, so they use a cold pack. So this is endothermic. A way to think about this is exothermic reactions get hot, endothermic reactions get cold. And one thing that we need to do is qualitatively be able to determine whether something is endothermic or exothermic. So we just want to determine if it's endothermic or exothermic, not necessarily how much energy is exchanged. So let's look at an example. Heating water to its boiling point. And so we don't have the answers in front of us. I do want to switch over to here. So heating water to its boiling point. The question becomes, do we need to put heat energy in or take heat energy away? Well, if we want to heat water up, we have to put heat energy in. So Q is positive. Delta H is positive. So these things are positive. This means that this is an endothermic process. So this, I'm just going to write endothermic. So this is endothermic. We have to add heat to cause water to heat up. Burning methane. Now, burning methane is one that confuses students, because if you want to start burning methane, you have to add a spark. And that adds what's called the activation energy. And that doesn't count. So think about what's happening while the methane is burning. Is heat being released or is heat being absorbed? Well, in this case, heat is being released when you burn methane. So Q is negative, delta H is negative, and this is an exothermic process. Ice melting. So if we have solid water and we want to turn it into liquid water, do we have to add heat or do we have to take heat away? Of course, if you want ice to melt, you have to add heat. So if you're adding heat for the ice, the system, Q and delta H are positive. So this is endothermic, because you have to add heat in order to get ice to melt. Finally, let's look at water vapor condensing on a cold glass on a summer day. So we have water in the air, which is water gas, forming water liquid. Well, if you want gaseous water to form liquid water, you have to take heat away. And to take heat away, if you take heat away, Q and delta H are negative. This is an exothermic process. So it's really important to practice with a few of these to determine if things are endo or exothermic. But the basic idea is, if you have to put heat in, like if you want to melt ice, it's endothermic. If you have to take heat away, like for example, if you want to turn gaseous water into liquid water, it is exothermic. So these are just some examples of this process. Now the next thing we want to look at is reaction enthalpy. And you've seen these types of diagrams before, but I just want to show you another one. Here we have methane plus 2 oxygen forming carbon dioxide and water. The enthalpy of methane and oxygen is relatively high. The enthalpy of carbon dioxide and water is relatively low. So when you perform this reaction, it releases 890 kilojoules of energy. Now what's really important to note is that 890 kilojoules of energy that's released is for the reaction as written. That's for 1 mole of methane, for 2 moles of oxygen, to form 1 mole of carbon dioxide, and to form 2 moles of water. The amounts are essentially the stoichiometric coefficients. Another important thing to note is, if you wanted to combine carbon dioxide and water to form oxygen and methane, you would have to put in 890 kilojoules of energy. So the magnitude is the same, but the sign is different. So the magnitude is still 890 kilojoules, but now it's positive instead of negative. So the reverse reaction has the opposite sign of the forward reaction. The other important thing to note, as I said before, is for the reaction as written. So let's take a look here at this example. Here it says how much heat energy is released if 14.8 grams of oxygen are burned with plenty of methane. So here we have grams of oxygen. Well, what we want to do is convert from grams of oxygen to moles of oxygen and then finally to kilojoules of heat energy, or enthalpy. Note that this is very much like the dimensional analysis you've done before, except now we have energy in it. So grams to moles we know how to do. 1 mole of O2 is 16 plus 16, or 32.00 grams of O2. Moles of O2 to kilojoules, again, is for the reaction as written. For this reaction, the delta H of it is minus 890 kilojoules. That means for 2 moles of oxygen, 890 kilojoules of energy will be released. Remember that the negative here just means released. The magnitude of energy that will be released, it asks how much will be released, is 890 kilojoules. So when it asks how much is released, it's not looking for the negative sign, it's just looking for the number. So let's take a look. If we take grams of oxygen, we're given 14.8 grams of oxygen, times, we want to convert it to moles, so we put the 32.00 grams of oxygen on the bottom, the 1 mole of oxygen on top. Then we want to convert to kilojoules. Well, we want moles of oxygen to cancel out, so we put 2 moles of oxygen on the bottom, because this is for the reaction as written, and then on top we put the 890 kilojoules. Multiply by the top, divide by the bottom, just like other stoichiometry you've done in the past, and you'll find that you get 206 kilojoules. What's important to remember is that this is the enthalpy of the reaction as written with the stoichiometric coefficients. This is very much common sense in everyday life. If you burn a lot of methane, you get a lot of energy. If you burn a little bit of methane, you get a little bit of energy. Said another way, the amount of methane that is burned, or in this case oxygen that is burned, is depending, or is going to determine how much energy is released. So we need to know how to read this. And again, it is for the reaction as written. So 2 moles of oxygen releases this much energy. 1 mole of CO2 being formed releases this much energy. 2 moles of water being formed releases this much energy. So this is for the reaction as written, and that's a very important concept. To reinforce that, I want to do another example. It says, according to the following thermochemical equation, what mass of water in grams must form in order to produce 975 kilojoules of energy? So this is very similar to the previous example, except here we're starting with the energy and we're looking for grams. In the previous example, we were going the other direction. We were starting with grams and looking for kilojoules. So in this case, we want to convert kilojoules to moles of, that should be subscripted. These are all not subscripted, must be when I pasted it in, it messed up the subscripts. But anyway, we want to convert from kilojoules of energy to moles of water. Why water? Because the question asks for the mass of water. Once we have moles of water, we want to convert it to grams of water. Now, the relationship between kilojoules and moles, as we talked about in the previous example, is 184 kilojoules of water is equal to the stoichiometric coefficient number of moles of water for the reaction as written. So 2 moles of water in this case. And then moles to grams, you may remember by now, 1 mole of water is equal to 18.02 grams of water. Now we can set up our stoichiometry, starting with 975 kilojoules of energy times. We want kilojoules to cancel out. I guess we don't really need water there. So we just put the 184 kilojoules down here and the 2 moles of water up here. Now that we have moles of water, we want to convert it to grams. We put the mole on the bottom so it'll cancel out. And we put the 18.02 grams of water on top, like so. Multiply by the top, divide by the bottom, repeat, repeat, repeat. And we end up with 191 grams of water. So when we round to 3 significant figures. So what's important to remember is that the stoichiometric coefficients tell us how much energy you'll get for a specific amount. So the enthalpy of the reaction is for the reaction as written. Now earlier we talked about how enthalpy is a state function. And what we're going to look at next is the enthalpy of formation. which is a definition that we can then use, because enthalpy is a state function, to determine a few other things. So let's take a look at a couple of these examples. First, we want to know what enthalpy of formation is. Enthalpy of formation is the formation of a compound from its elements. And there's two things you need to know. First, the enthalpy of formation of elements is by definition 0. Second, you must form 1 mole of the compound exactly. So the units for enthalpy of formation are kilojoules per mole. So that's basically what the two things that we need to remember for enthalpy of formation. So it's the formation of the compound from its elements. The enthalpy of formation of the elements is 0, and the product must be 1 mole of the compound. That way the units for all enthalpies of formation can be kilojoules per mole, instead of us having to figure out or know the stoichiometry of all formation reactions, which would be too much of a pain. So that's basically that. So if we look at water, for example, water is formed from its elements, oxygen and hydrogen. The enthalpy of formation of hydrogen is 0. The enthalpy of formation of oxygen is 0. Notice that we have a weird thing here. We have a fractional coefficient. We have half of an O2. That's because there's 1 oxygen in water. Note that the stoichiometric coefficient of water has to be 1, because we're forming 1 mole of product. In order to form 1 mole of product, we have to use half of an O2. So fractional coefficients are allowed in enthalpy of formations. Let's do a couple of examples. What is the enthalpy formation reaction for lithium nitrate? Well, let's figure out what lithium nitrate is first. We have Li plus and nitrate is NO3 minus. We cross them and we get LiNO3. And the standard state is a solid for lithium nitrate. Now, we're going to form 1 lithium nitrate. Well, what elements are we going to use to form lithium nitrate? The first is lithium, which happens to be a solid. If you're not sure, you can look up in a table, which you can find online, standard enthalpy of formation table, and look for the one where the enthalpy of formation is 0. That is the elemental form. I should note that in some cases it's kind of weird. So if you look at carbon, it's solid graphite. And again, if you look this up on a table online, standard enthalpy of formation table, you'll find that the formation is 0 kilojoules per mole. Sometimes it's obvious, like oxygen is diatomic in a gas, bromine is diatomic in a liquid. Other times it's solid graphite. So that's just something you can look up on a table. It won't come up on a test or anything like that. So if we look at lithium nitrate again, lithium nitrate we're forming as a solid from its elements. So the first element we need is lithium. The second element we need is nitrogen, but nitrogen is a diatomic gas. And the last element we need is oxygen, which is also a diatomic gas. The enthalpy of formation of lithium, nitrogen, and oxygen are all 0. The enthalpy of formation of lithium nitrate is not. I should point out that that's by definition that elements have an enthalpy of formation of 0. So, now we need to balance this such that this stoichiometric coefficient must be 1. So whatever the enthalpy of formation of lithium nitrate is, it has units of kilojoules per 1 mole, or just kilojoules per mole. So we need 1 lithium, 1 lithium. For nitrogen, there's only 1 here. So we need half of an N2. And for oxygen, there are 3 of them, and we have O2, so we need 3 halves, or 1.5, but it's usually written as a fraction, O2s. So here is the standard enthalpy of formation for lithium nitrate. Let's try it again for sodium carbonate. In the case of sodium carbonate, we have Na plus CO3, 2 minus, cross them, and our product is Na2CO3, and it's an ionic compound, so it's a solid in its standard state. So here we need to find the elements that we need to make sodium carbonate. Well, the first element is sodium, which is a solid, plus carbon, which is solid graphite, which is what I mentioned before, plus oxygen, O2, gas. Now, for enthalpy of formation reaction, a couple things to remember. Formation from the elements, we did that part. Now we need to remember that we need to form exactly 1 mole of the product. So how can we form exactly 1 mole of the product? Well, if we have 2 sodiums here, we need 2 sodiums here. We have 1 carbon, we're good. Oxygens, we have 3. This is O2, same as in the previous example. We need 3 halves of an O2. And this is the enthalpy of formation reaction for sodium carbonate. Now that we've seen enthalpy of formation reactions, let's see how we can use enthalpy of formations and the fact that enthalpy is a state function in order to determine the enthalpy of other reactions. And the real convenience that we have here is that basically we have this reaction. And this is the enthalpy of formation, or excuse me, the enthalpy of a reaction equals the summation of N, the number of moles, times the enthalpy of formation of the products, minus the summation of N times the enthalpy of formation of the reactants. And these are in their standard states, and I'm not going to get into what standard states are here in general chemistry. You will talk about that more in like a physical chemistry course. So here we have this enthalpy of reaction equation. But let's think about what this equation is actually saying. What it's saying is we are going to destroy the reactants back into their elements. So we're going to do the opposite of an enthalpy of formation reaction. We're going to take any compounds that we have and we're going to form it back into elements. So we take the negative of the enthalpy of formation of the reactants. We then add that to the enthalpy of formation of the products, because what we're going to do is we're going to take those elements, we're going to recombine them to form the products. Because enthalpy is a state function, this works. We take the reactants, we destroy them into their elements, we recombine those elements in order to form the products. Now let's take a look at how this can actually work. Well, let's look at this reaction. It says, use the information provided to determine the enthalpy of reaction for this reaction below. We have CH4 plus 4Cl2 yields CCl4 plus 4HCl. And I apologize, I pasted these in from another source and the subscripts didn't come in. So we want to find the enthalpy of the reaction. So what we need to use is delta H in the standard state of the reaction equals the summation of N, the number of moles, times the enthalpy of formation of the products minus the summation of N times the enthalpy of formation of the reactants. So this is the equation we're going to use. So again, we're going to take CH4, decompose it into carbon and hydrogen. We're going to take Cl2, it's already an element, so we don't have to do anything. We're then going to take that carbon, hydrogen, and chlorine and combine it to form CCl4 and HCl. So the products have a positive enthalpy of formation because we're forming them, and the reactants have a negative enthalpy of formation because we're essentially destroying them back into their elements. So the first thing we want to do is find the first product, and you'll notice the enthalpy of formation are given here. You can also find these on tables online or in textbooks. So here we have the enthalpy of formation of the products. The first product is CCl4. We are forming one of them. Note, we do have to multiply by the moles because the enthalpy of formation is for the formation of 1 mole. If we form 4 moles, like in the case of HCl, we need to use 4 times as much. So again, the first product is CCl4. So this is minus 96 kilojoules. Plus, the second product is HCl, and there are 4 of them, so 4 times minus 92 kilojoules. Minus, the first reactant that we're going to destroy is CH4. So instead of minus 75, we're going to take minus 75, which will eventually be plus 75 kilojoules. And again, there's only 1. For Cl2, you'll notice that it's not given on this enthalpy of formation table. And the reason for that is it is itself an element. So its enthalpy of formation is 0. If you want, you can put plus 4 times 0, or you can just leave it blank. When you do all this math, you find that this is minus 389 kilojoules. Now, for the next reaction, the reaction that we want to study is IF7, which is a gas, plus I2 solid, yields IF5, which is a gas, plus 2IF, which is a gas. So this, we want to find the enthalpy of formation, or the enthalpy of the reaction. We're going to use the exact same equation. Delta H reaction equals the summation of N of the enthalpies of formation of the products minus N times the enthalpy of formation of the reactants. So same equation, just a different application. So let's find the first product. The first product is IF5. There's one of them, so it's minus 840 kilojoules. We don't need to multiply it by anything because there's only one. The next case, we have 2IF. So we add to that 2 times negative 95 kilojoules. Then we take that entire answer and we subtract the enthalpy of formation of IF7. There's 1, so we just put in ones, negative 941 kilojoules. And again, we have an element, I2, so you could do plus 0 or just leave it blank. When you do this math, you find that the enthalpy of this reaction, for the reaction as written, is minus 89 kilojoules. So this is how we use the enthalpy of the products minus the enthalpy of the reactants to use enthalpies of formation in order to find enthalpies of reactions. And again, you can do this because it's a state function like altitude. It doesn't matter which path you take to climb the mountain, your altitude change will be the same, independent of the path. Another way that we can do this, use this to our advantage, the fact that enthalpy is a state function, is something called Hess's law. So let's look at this. Hess's law essentially allows us to add reactions together to determine the overall enthalpy of a greater reaction. So let's look at this example. Here we have carbon plus oxygen yields CO2. The enthalpy of this reaction is minus 393.5 kilojoules. Here we have carbon plus oxygen yields CO plus half an O2, this intermediate reaction. This is minus 111 kilojoules. If we then take the CO and we add half an O2 to it and we form CO2, that will release 282.5 kilojoules. If you notice, this step plus this step, 111 minus 111 plus minus 282.5 equals minus 393.5 kilojoules. So if we add intermediate reactions that yield the same overall reaction, we can figure out the enthalpy of reaction. And sometimes in thermodynamics, it's extremely difficult for practical reasons to measure the enthalpy of a process. So the best we can do, or another way of doing it, I guess I should say, is to measure some of the intermediate processes and then add them up and find some other intermediate process or find the overall. It just depends on the case that you're dealing with. But it allows us to predict something about steps of reactions or other pieces of reactions that are very difficult to measure, usually for practical reasons. So we can use Hess's law. I want to do a couple of examples of where we used Hess's law, including this one, because there are some practical steps that theory doesn't discuss particularly well. So for the first one, I want to actually use a piece of paper because I don't have it written out as a partial example. So let me take a look here. Just give me 1 second to get organized. What we're going to look at is that reaction we were just looking at. We have C solid plus O2 gas yields CO2 gas. And we want to know the delta H of this reaction, and we don't know what it is. But what we do know is the two intermediate steps. Of course, we do know what it is because it's on the previous slide, but this is just an example. We do know the enthalpy of the reaction of the two previous steps. And the steps are, step 1, C solid plus half of an O2 gas yields CO gas. And we know the enthalpy of this reaction equals minus 111 kilojoules. And we'll call this reaction 1. For reaction 2, we know that CO gas plus half of an O2 gas yields CO2 gas. And we know that the enthalpy of this reaction equals minus 200, let me rewrite this, minus 283 kilojoules. So we know the enthalpy of these two partial reactions, which can overall add up to be this reaction. So in this case, we can directly add these two reactions together. And the way I know that is I can see that there's one carbon, there's half an O2 plus half an O2, which gives me one O2. There's a CO on this side and a CO on this side, so it will cancel out. And there's a CO2 as the product. So I can directly add these reactions together. Sometimes you can't, but in this case, we can directly add the reactions together. So how do you add reactions together? Well, to do that, you take everything on the reactant side and you put it all on one reactant side. And you take everything on the product side and you put it on one product side. So let's do that. So when we add these together, we get C solid plus half an O2 gas, so these reactants, plus these reactants, CO gas plus half of an O2 gas. So I roll all four reactants on one reactant side. Now I write both products on the product side. CO gas plus CO2 gas. Notice I kept all of the stoichiometric coefficients the same. This one was 1, this was half, 1, half, 1, 1. So I literally just wrote all these on the reactant side and all these on the product side exactly as they were written before. States of matter the same, stoichiometric coefficients the same. Now I have to do two things. One, cancel out things that are on both sides, because if something's both a product and a reactant, nothing happens to it, and that's not chemistry. It shouldn't be in the chemical reaction. The second thing I need to do is combine like terms. So reading from basically left to right, I notice that carbon is only here once on the reactant side and it's never on the product side. So I can just leave it. Half an O2, I notice I can combine it with the other half of an O2. So I combine these together and half plus half gives me a whole 1 O2. Now I'm looking at CO. CO, I notice, is on both sides, so I can get rid of it. CO2 is only on the product side. So when I combine this, I get carbon solid plus my whole O2 gas yields CO2 gas. So I get the overall reaction. You'll notice that this overall reaction exactly matches the original reaction. Now if I add the reactions, I also add the enthalpies. So I take the minus 111 kilojoules and I add it to the minus 283 kilojoules and I get minus 394 kilojoules, which means the delta H of this overall reaction is equal to minus 394 kilojoules. And again, the enthalpies of reactions are for the reactions as written. 1 carbon, 1 oxygen, and 1 CO2 in this example. 1 mole of, I should say. Let's look at another example of Hess's law that isn't quite as straightforward. So here, I want to calculate the enthalpy of the reaction for this product. So my goal is to find delta H of the reaction. What is that equal to? So that's my goal. And I have the following information. I have N2 plus O2 yields 2NO, and I have the enthalpy of the reaction. I'm going to call that reaction 1. I also have NO plus half an O2 yields NO2, and I'm going to call that reaction 2, and I have the enthalpy of that reaction. So now I need to decide, well, what do I need to do to these reactions to make it equal this overall reaction? The first thing that I want to do is look for some common things in order to try to figure out the best way to do this. So if I look at nitrogen Here I notice that nitrogen is only in this compound. There's nitrogen is nowhere else. And there's one nitrogen and there's one nitrogen. Two things to notice. One, the nitrogen is on the reactant side. If it's not on the reactant side, I may need to reverse the reaction. If I reverse the reaction, I reverse the enthalpy. But I don't need to do that here because it's already on the reactant side. The other thing I notice is there's one nitrogen here and one nitrogen here. So probably reaction 1 is good to go because it has the only nitrogen which is on the reactant side and it's the proper number. Oxygen is tricky because I notice that I have an oxygen in both reactions. So I'm going to skip oxygen for right now. NO is tricky because NO is not in the overall reaction. So I'm going to skip it for right now. What you're going to find when you're doing these problems is that they work out nicely because they're examples that are designed to work out nicely. Sometimes this is much more challenging and even impossible. But here, they're going to work out nicely. So again, I skip NO because it's not in the overall reaction. That just leaves me with NO2. So what I notice is that NO2 is on the right side, which is good because I want it to be a product. The problem with NO2 is here I have 2 and here I only have 1. So in order to get 2 NO2s, I need to double this reaction. So for reaction 1, I decided not to do anything. And how I decided that was based on nitrogen. Because nitrogen is only in this reaction, it's on the reactant side, and it has the correct stoichiometric coefficient. Sometimes you do need to reverse the reaction if it's on the wrong side, and sometimes you need to double, triple, whatever if it's the wrong number. But in this case, I don't need to do anything. So I'm just going to rewrite reaction 1 exactly as written. And I'm going to keep the delta H exactly as it is. For reaction 2, for the reason mentioned before, NO2 is on the correct side. It's a product. It's unique to this reaction, but there's 2 here and only 1 here. So I need to double this reaction. If you double a reaction, you have to double everything. So not NO, 2NO gas plus half an O2 plus an O2 times 2 is O2 gas yields 2NO2 gas. If I do this reaction twice, I have to double the enthalpy. So delta H is not minus 57.06. Instead, it's minus 114.1. Now I can add these reactions together. Remember, to add reactions together, everything on the reactant side goes on the reactant side. Everything on the product side goes on the product side. So I do N2 gas plus O2 gas plus 2NO gas plus O2 gas yields 2NO gas plus 2NO2 gas. Combine like terms and cancel the same thing on both sides. The first like term is oxygen. So I have 1 oxygen and 1 oxygen. That becomes 2 O2 gases. There's 2 NOs on this side and 2 NOs on this side, and as I mentioned before, these do tend to work out nicely. Now I can rewrite N2 gas plus 2 O2 gas yields 2 NO2 gas. If I added the 2 reactions, I have to add their enthalpies. So the enthalpy of the reaction is this one plus this one. When you add those two together, you get 66.4 kilojoules. Remember, that's for the reaction as written. Nitrogen, 1 mole of nitrogen, 2 moles of oxygen, and 2 moles of NO2. So the Hess's law and enthalpies of formation, which is just another form of Hess's law, are 2 ways in which we take advantage of the fact that enthalpy is a state function. Enthalpy is extremely important in this chapter and in chemistry, and these Hess's law problems, enthalpy of formation problems, finding the enthalpy of a reaction based on a mass of some reactant or a mass of some reactant or product based on an enthalpy, all this stuff takes practice. So it's really important to practice all of these different thermochemical examples because these are the different thermodynamic properties that chemists take into consideration when they study chemical reactions.